Hello and welcome to Principles of Mathematics, lecture number 4. In this lesson, we're going to look at another fundamental concept in mathematics, and that is the concept of sets. Last time we discussed symbolic logic, and together with set theory, they pretty much lay the foundations of all modern mathematics. Some of the topics we're going to look at are set language and structure, the connection between finite sets, and another important concept called one-to-one correspondence. Much of the credit for set theory goes to one brilliant mathematician named George Cantor, who created the theory, and it ended up having a very, very profound effect on all of mathematics. We can use sets and the relationship between them as great learning tools for elementary education and describe concepts such as less than, as well as some of the operations in basic arithmetic can be described using sets as well. We will get to all that shortly. Let's go ahead and start with what a set is. A set is any well-defined. Notice that this is italicized for a reason because it's very important. Any well-defined group or collection of objects. So basically a bag with some items in it, right? So why is the well-defined aspect so important? There has to be a way for you to determine whether an element belongs to a set or not. So for example, if I say the set of cool people in your class, right? That would not be a well-defined group because we don't have a fixed definition for what it means to be cool, right? So that would not, constitute a mathematical set. However, if I say the set of all students in our class, for instance, that's a well-defined group. In fact, I can refer to my roster at any time and come up with the exact members, and we can tell, with enough information whether an individual belongs to that set or not. The objects that belong to a set are called the elements or members of the set. You can use those terms interchangeably. One method for denoting or basically just showing a set is to simply list the elements inside braces, and these are called braces. Some people call them curly brackets, but the more proper name for them is braces. And we use a label which by agreement is a capital letter. Okay, so we've agreed to use capital letters to prevent confusion. All right, so these are the basics as far as definition of a set is concerned. Here are some important properties you have to pay attention. Each element of a set should be listed only once. So that means you don't want to do this. You don't want to say A, for example, is the set 1, 2, 4, 1. Okay? That would not be the simplest form of that set. What you would want to do is write those ones only once. So in other words, this is exactly the same as this set. So we do not repeat elements inside a set. Now notice that this is going to become important later, because if somebody asks you how many elements does this set have, if you were to say 4, you would be incorrect. So you would always have to have the simplest form of a set with no repetition before you can determine the number of elements in that set. In other words, yes, can you write this? Yet you're not, necessarily breaking any monumental rule, except that this would just not be in simplified form. This would be the correct form of it, and we stay away from that form. Now, the order of the second thing to pay attention to is that the order of elements is unimportant. Remember, you're putting some groceries in a bag, for instance, right? Does it matter which one falls where in the bag? No, the order doesn't matter, but you know exactly what the contents of the bag are, and that's what's important. So in other words, this set that we have here, 1, 2, 4, I could have easily have written it in any order. I could have written it as 2, 1, 4. Same thing, no problem. Or I could have written it as, for example, 4, 1, 2, or any permutation of those three numbers. They're all the same set. They all contain the numbers 1, 2, and 4. Now, we symbolize the fact that an element belongs to a set using the symbol epsilon. Now, this is the Greek letter epsilon, and we use an epsilon with a cross through it to say that an element does not belong to a given set. Now, notice that I named this set here A, right? So we notice that, for example, 1 belongs to A, right? So that's how we write it. So when you read that, you can either say 1 belongs to A, or you can say 1 is a member of A. Or we can say, notice, 2 is also an element of A or a member of A, or you can say 2 belongs to A. Now, we also notice that, for example, 5 does not belong to the set A. So we use that notation, the epsilon with the little bar through it, or line through it, to show that it does not belong to A. And lastly, what I already mentioned in our last slide is the fact that the set must be well defined. We must be able to tell whether or not any given object belongs to that set, to a given set or not. All right? We have two main methods of describing sets. The first method is the obvious one, where you just list the elements, right? So that's, the modern name for it is listing method. We used to call it the roster method. We can still use that name. It's still in usage. So basically, the roster method is very simple. Just use braces, and within the braces just list all the elements. And if possible, sometimes sets don't have a finite number of elements, such as the set of natural numbers, which we indicate using n. Now, this capital N is usually, when you look inside a textbook, is written in bold and oftentimes in script letter. Now, when you're writing on paper, what we do is we double bar the left side like that, so that we can tell it's not just any N. So when we see the N, capital N, with the double bar on the left side, we know that we're looking at the set of natural numbers, which is basically all the numbers you can count on your hands, starting with 1 and then 2, 3, 4, and on forever, right? So notice this set has infinitely many elements, so you can't list them all, correct? However, since there's a pattern that continues, you can just use 3 dots to indicate the continuing pattern. This set of 3 dots is called an ellipsis, okay? And here, notice, here it looks like we're looking at a set L, which contains all the alphabet, right? So even though there's an ellipsis here, we know that this is not an infinite set. So in this particular usage, you have to make sure that you don't mistake this for an infinite set. But this one is, because there is no end to that particular pattern. The second method for describing sets is called set builder notation. Why? Because you don't actually list the members of the set, but you basically describe how to obtain the members of the set, or how you describe them in a way that anyone looking at that description will then be able to write the listing method or the roster method notation for the set. So the way you read this notation is the following. You say all x such that x belongs to n, or the set of natural numbers, and x is less than 5, right? So pause the video, think for a minute, see if you can actually write that in the roster method. Remember, here we're just giving you description or a description of how to build this set, right? How to build the roster method of this set. So see if you can come up with that and then come back. Okay, so I think you realize that here we're just looking at all the natural numbers. Let's remind ourselves what they are. Remember, the set of natural numbers starts with 1 and then 2, 3, 4, and on, right? So we're looking at all the natural numbers that are strictly less than 5, okay? So that would be 1, 2, 3, and 4, right? So we can write this set just like that. And that's it. Those are the only elements that are in that set. Now be very careful with the inequality because it's kind of subtle. If this were less than or equal to 5, in other words, if I were looking for another set D, which was the set of all x such that x belongs to n. And by the way, instead of the and, sometimes we just use a comma. We don't even have to write and x is less than or equal to 5, then this would be a different set, right? This would have one more element. It would have 1, 2, 3, 4, and 5 in it, because we're interested in all natural numbers that are either less than or equal to 5. So this time 5 is included in the set. All right, in this example, we're looking at two very famous sets. As you can see, in the first set, we have all the even numbers, and in the second set, well, even natural numbers, and in the second set, we have all the odd natural numbers, right? So we want to see if there's any way we can write these using a set builder notation, right? So let's remind ourselves what the set of natural numbers is, and as we know, that is n equals 1, 2, 3, 4, 5. All right, so if I look at a typical element n belonging to the set of natural numbers, and let's say that an element in here I call x, right? What would have to be the relationship between x and these members of the set of natural numbers, right? Notice that if I take each of these natural numbers and I double them, I end up with these numbers, right? 2 times 1 is 2, 2 times 2 is 4, 2 times 3 is 6, 2 times 4 is 8, etc. So if I have x equals 2n, I should be able to use that in my set builder notation. And that is exactly what this is going to be. So it's going to be all x such that x equals 2n, and in this case, we have to specify what n stands for. N belongs to n. That means n is any natural number. So there is a description for the set of even natural numbers. Now, of course, if you prefer words, you can also say that's the set of all x such that x is an even natural number. All right, like that. Okay, how about the set of odd numbers? So we just realized that if we basically want to create even numbers, we can do it by doubling a natural number, right? We realized that there. So what are we going to do to create the odd numbers? Well, every time I double, right, I'm going to create, so starting with n equals 1, right? Let's look at n equals 1. If I just double n, I get 2 times 1, right? But if I want to get the first element in here, that's too much, right? So what am I going to do to get 1 from 2 times 1? I'm going to have to subtract 1, okay? This is one of the standard ways in which we create odd numbers. Now, if we were dealing with the set of whole numbers, we could have started with 0, in which case we would have had 2 times 1, 0 plus 1. But again, that's just an alternate way, but we're only dealing with the set of natural numbers, so we have to deal with numbers that start with 1. So in that case, we have to subtract the 1, and the general form will be 2n minus 1. Now think about it. 2n equals 1 gives us 1. n equals 2 would give us what? Would give us 2 times 2 minus 1, which is 4 minus 1, which is 3, right? N equals 3, for instance, will give us what? 2 times 3 minus 1, which is 5. So you see, in this way, we obtain all the odd natural numbers. So here we're going to say all x such that x equals 2n minus 1. And again, we have to specify the fact that n belongs to n. Okay, of course, lowercase n belonging to this script n, which stands for the set of natural numbers. All right, and again, just like in the previous case with the even numbers, we could always just say the set of all x such that x is an odd natural number. But as you've probably guessed, in mathematics, we always go for the really efficient language which uses as little writing as possible. In reality, pure mathematicians are usually very lazy writers. That's one of the reasons they went into pure mathematics, because they can say a whole lot with just a few symbols. All right. So note that the conversion that took here was from the listing or roster notation to set builder notation, right? All right. In mathematics, when we show you how to go from point A to point B, you can count on the fact that later we're going to ask you to go back from point B to point A. So here we're going to do the exact opposite. Here we're given a set in set builder notation, and we're asked to go ahead and list its element, meaning go to the listing or roster notation. All right, so here we have the set A is the set of all elements of the form 2k plus 1 such that k equals 3, 4, or 5. So this is a very, very limited and finite set. You're only going to run through 3 values of k, namely 3, 4, and 5 in this expression. So you just go ahead and start running through it. So the first, so we have 2 times 3 plus 1, which gives us what? 6 plus 1 is 7. Then we have 2 times 4 plus 1, which gives us 9. And we have 2 times 5 plus 1, which gives us 11. So that's it. Those are the only 3 members of this set. So all you have to do is you have to write a set containing 7, 9, 11. Now, oftentimes, just for the purpose of clarity and ease of check, I may write sets in ascending order of largeness, but notice that it does not matter at all. In other words, had you written 11, 7, 9, that would have been just as well. And also remember that we separate the members of a set using commas, right? Not semicolons, nothing like that, just commas. All right. If you want a more kind of organized, tabularized version, what you could do is you could make a table and just say for k value equal 3, the value of 2k plus 1 becomes, for example, 7. For k value 4, the value of 2k plus 1 becomes 9. For the k value 5, the value of 2k plus 1 becomes 11, like that. Okay? So that's that. Very simple. All right, so here's one that you should be able to handle. Go ahead and pause the video, see if you can come up with the roster method version of this particular set, which is given to you in set builder notation. All right, so as you can see, we have some restrictions, right? The number has to be positive. That's a little bit of a moot point, right? Because we know that all natural numbers are what? Are positive, right? They start with 1. So not as important as the next requirement, that it has to be even, right? So we want positive, even natural numbers less than 8. So we're looking at the first even positive natural number is 2, right? What's the next one? 4 and 6. And that's it. Remember, this is strict inequality. It has to be strictly less than 8. So we stop right there. Now, again, had this instead asked us to find all positive even natural numbers less than or equal to 8, we would have included 8 in the set as well. Now we want to get into discussions about how we can compare sets, right? Well, the simplest kind of comparison would be under what conditions are two sets equal, right? And that's only possible if they contain exactly the same elements. Again, remember the order makes no difference. And if two sets are equal, we just use the regular equal notation. Notice that if two sets are equal, then of course every element of A is contained in B and vice versa, right? Every element of B is contained in A. Now, if two sets are said not to be equal, right? Remember that there has to be at least one element that is not contained in both of those sets, okay? So let's take a quick look at an example. Suppose I say to you, A is the set 1, 2, 3. B is the set 3, 1, 2. What can you tell me about those two sets? Are they equal? Absolutely, right? Because we don't care about the order. And if we don't care about the order, these two sets are indeed the same because they contain the same elements. So here we can say A equals B, right? Now, if I had another set, C, which also contained the element 4, we notice that A is not equal to C and B is not equal to C either. Because remember, the requirement for inequality is that there is at least one element that's not in both of those sets. 4 is not in both A and C, and 4 is not in both B and C either. So those, neither A and C can be equal, nor B and C. All right. Okay, one of the important concepts in set theory is the notion of one-to-one correspondence. Basically, if the elements of two sets A and B can be paired so that for each element of A, there's exactly one element of B, and for vice versa, for each element of B there is exactly one element of A, then the two sets A and B are said to be in a one-to-one correspondence. Let's look at a real simple example. Let's say we're dealing with the set 1, 2, 3 and the set ABC. Notice here are a couple of really simple one-to-one correspondences, right? We can match 1 with A, 2 with B, 3 with C, right? Or we could match 3 with A, 2 with B, and 1 with C, right? One interesting question that comes up is, how many possible ways are there to create this correspondence? And that's what we want to look at next. Here are a couple of very systematic ways of dealing with that. So we write one of the sets like 1, 2, and 3 and just run through all the possible ways they could be matched with A, B, and C, right? For example, suppose A comes first. In other words, suppose A is matched with 1. That means we can have B2 matched with B and 3 matched with C, right? Or keep the A fixed, we could do the other. We could send 2 to C and 3 to B, right? Then we move on to B, right? So what if we start with B, right? What are the possible pairings available for 2? Well, it could go to A and 3 to C, or vice versa. 2 can go to C and 3 can go to A, right? And then we take care of this pairings of A1 with C, right? If 1 is paired with C, then 2 can either be paired with A or B, right? And the same with 3. So you can see there are 6 possible ways. Another way of showing it is a tree diagram, right? So 1 can either be matched with A, which means 2 can be matched with B and 3 with C, or 2 can be matched with C and 3 with B. Same thing for the other 2 elements. So both of these diagrams are kind of visual ways of seeing the possible number of one-to-one correspondences. You can see that if the number of elements increases, this is going to get pretty large. So we're going to see if we can come up with a better way of coming up with the number 6 if possible. All right, so how can we determine the number of one-to-one correspondences between these two sets? Well, in this particular example, given the element 1 in the first set, how many possible elements are there in the second set that it can be paired with? There are 3, right? Namely, it can be A or B or C. Now, let's assume you've made that choice, right? Let's say you've paired 1 with with 2 of those, right? Because this has to be a one-to-one correspondence, when you move on to try to pair 2 with some element from the set of A, B, and C, then you don't have 3 choices anymore, right? Because 1 has already been spoken for by 1. So now you only have 2 choices, right? And let's say that now you've made both of those choices and it's time to pair 3 with one of the letters A, B, or C, right? Now remember, 2 of those letters are already spoken for by 1 and 2, right? So now you only have 1 choice, right? So for a total of what? 3 and 2 is 5 and 1 is what? 6. Now, this brings us to one of the most important concepts in counting, which we call the fundamental counting principle. If one event, let's say event M, can occur in M ways, notice capital M and lowercase m, so there's no confusion, and after it has occurred, another event N can occur in N ways, then event M followed by event N can occur in M times N ways. Okay, so that is a very, very useful way of saying this. So let's see if we can put this in the context of the example we were looking at. So let's say the first event is pairing 1 with one of the members of the set ABC, right? And the second event being pairing 2 with one of the members of that set. A, B, C, and event 3 being the pairing of 3 with one of those 3 letters, A, B, or C. Then we notice that there are 3 ways you can do the first one, right? One can either be paired with A, or it can be paired with B, or it can be paired with C. So there are 3 choices here. Notice with the counting principle, we're going to multiply that. So let's say that choice has already been made. So for event 2, now we no longer have 3 options to pair 2 with, because 1 has already been taken by 1. Let's say I paired 1 with A, for example, right? That only leaves 2 letters, B and C, for 2 to be paired with, right? So how many ways can 2 be paired? 2 ways. Now, once that's done, right, remember 2 of the letters are now spoken for, so there's only 1 letter left that can be paired with 3. So there's 1 way that can be done. So now if we multiply those 3, we get 6, okay? Now, this, by the way, is given to you just for 2 events, but it can be done for any finite number of events, right? So you can have event A, B, C, all the way to whatever letter you like. And you just multiply the numbers like that, and you end up with total number of ways that these events can happen in order, right? Remember that. So the first event first, then the second event, then the third event, on and on, as long as you need. Okay, we already discussed the notion of equality of sets. The next thing we want to do is look at another way of talking about 2 sets, and that's the notion of equivalence of 2 sets. For this, we use this the tilde symbol like this. So we say A is equivalent to B, and this can only happen if there's a one-to-one correspondence between the sets. So we already saw, for example, that there is a one-to-one correspondence between the elements of 1, 2, 3, the set containing 1, 2, 3, and the set B containing the letters A, B, and C, right? So obviously these 2 sets are not equal, because remember, 2 sets are only equal if they have the exact same members. Here we obviously don't, right? However, there is something interesting about them, right? We can put them in a one-to-one correspondence. And notice that the only way that can happen is if they basically, if at least for finite sets, right, is if they have the exact same number of elements, right? That's called cardinality. We're going to get into that in just a few minutes, but just keep in mind that as long as 2 sets have the same number of elements, they should be equivalent. So here we can say A is equivalent to B. All right, and that notice an interesting notion when it comes to equivalence and equality. Notice that obviously the fact that 2 sets are equivalent does not imply that they have to be equal, right? Just as the case here. But notice that if 2 sets are equal, then they are necessarily also what? Equivalent. So obviously if 2 sets are the same, you can put them into one-to-one correspondence with each other, right? The simplest way being just send each element to itself in the other set, right? So always keep in mind, and please don't just try to memorize this, understand it, that equality does imply equivalence. Using the language of logic from yesterday, what we would say is that if 2 sets are equal, then those 2 sets are what? Equivalent. But notice that the converse equivalence does not imply equality. Just because 2 sets are equivalent, it does not imply that they have to be what? um, equal. Now, does when we say something like this, do we mean that's never the case? No, absolutely not. Remember, mathematics, that's a very high bar for wanting to make a statement as a general statement. All that means is there are at least one set of equivalent sets that are not what? Equal. And we have that right here, right? So if somebody comes to you and says, "Hey, I just discovered if two sets are equivalent, then they're equal," right? Remember, all you need to do to show that that claim they're making is false is show them one counterexample. So you could just show these two sets and say, "Look, here we have two sets that are equivalent, but they're obviously not what? Equal," right? All right. So there's that. So here we have four sets, A, B, C, and D, and we want to compare them in the sense of equality and equivalence, okay? So let's kind of be systematic about it. So let's compare A with B, then we'll do A with C, then we'll do A with D, and then we'll just move on to B. We'll do B with C and B with D, and then we'll finally do C with D. Okay, so looking at only A and B, what can we tell? Are they equal? Clearly not, right? Are they equivalent? Well, remember, in order to be equivalent, there would need to be a one-to-one correspondence, which means they would have to have the same number of elements, but they don't. This one has 4 elements, this one has 3 elements. So A and B are not only not equal, but they're also not equivalent. So we can say A does not equal to B, and A is not equivalent to B either, right? Now bring your attention to A and C, right? Same exact scenario, right? They're not equal, obviously. They don't have the exact same elements, and nor are they equivalent because this one has one more element than that one, right? So we say A does not equal to C. This one is a little bit, should be a little bit more slanted right there. All right. And we also know that they're not equivalent, so A is not equivalent to C either. How about, so we move on to B and C. So are B and C equal? Clearly not, because they have what? They have different elements, right? Their elements are not all the same. However, we notice that they do have the same number of elements, so we can put them in a one-to-one correspondence, right? So B and C are definitely not equal, but do notice that B and C are, in fact, equivalent, okay? So now let's move on to B and D. Now, B and D, are they equal? Yeah, the orders are the same, but they have the exact same elements, don't they? So B and D are equal. Now, do I even need to think about whether they're equivalent or not? Not really, right? Because we know that if they're equivalent, they're equal, they're obviously also what? Equivalent. So oops, D. All right, so B and D are both equal and equivalent, right? Now we move on to the last pairing, C and D. Are they equal? Clearly not, but can they be put in a one-to-one correspondence? Do they have the same number of elements? Yes, they do. So C is not equal to D, right? But C is equivalent to D. See, so if you're just clear and systematic about these procedures, you won't miss anything and you will get them all in the right order. All right. Well, Not that they have to be done in a certain order, but I mean in the right way, I guess. All right, so let's move on to another example. Make sure you understand this and you're comfortable with it before we proceed. Okay, the next topic we want to discuss is what's called the cardinality of a set, or also referred to as the cardinal number of a set. And basically, the notation that we use, we put lowercase n and then in parentheses the name of the set. This indicates the number of elements in the set. Okay, so let's take a quick look at these sets. So let's say the set K includes these numbers 3, 5, 8, 0, and 11. So we want to know the cardinality. So we write n of k equals, notice there's 1, 2, 3, 4, 5 members. So the cardinality of k is 5. How about this set containing the element 0? Now, a lot of students incorrectly think, oh, this one has no elements. Yes, it does. 0 is as important as a number as any other number. Yes, it is one element and it is the number 0. So the cardinality of L is actually 1. How about this set? The set of all x such that x is a real number and x equals x plus 1. Now, that's an interesting question, right? Because can you think of any number that can satisfy this? Any real number? In other words, can you think of any real number that is the same as itself plus 1? How can that be? Well, if you take any real number, let's say we take 2, right? What happens if you add 1? That becomes 3. That's a completely different number, so they're not equal, right? You can do that with any real number. Take 0, right? And what happens when you add 1? Well, it becomes an entirely different number, 1, so they're not equal. It doesn't have to be all nice numbers either. Take, say, pi. Well, if you add 1 to pi, that's certainly not going to be close to 3.14 anymore. It's going to be more like 4.14, right? Again, they're not equal. So how many elements are in this set, which is all the numbers that satisfy this, right? There are none, okay? So now is when you say the number of elements of this set is 0, because there are no elements in that set. Now this symbol here, the big O and the bar through it, that's called the empty set. It's also called the null set. Now, one way of writing it is that. There's another way of writing it, which is just to use braces and put no members inside, just leave it blank inside. And these are both representing the same set, okay? So how many elements are there? Once again, none. So what's the cardinality of the empty set? Basically 0, okay? So that's how you deal with cardinality. All right, that brings us to the notion of finite sets as opposed to infinite sets, right? A finite set is basically a set whose cardinality, which means what? The number of its elements, is either a 0 or a natural number. Now, this actually brings us to the definition of a new set of numbers, which we call the whole numbers. The whole numbers is a set created solely out of respect for 0, okay? Because it's almost exactly the same as the set of natural numbers. You know that the set of natural numbers is the set containing 1, 2, 3, etc., right? The set of whole numbers brings in just one more element, namely 0. Notice the double barring on the left side. We do that for the set of whole numbers too. In fact, we do it for all the important subsets of the set of real numbers, or even larger sets like the set of complex numbers. All right. A set is finite if its cardinality is 0 or a natural numbers. Another way of saying that is that the cardinality is a whole number, okay? Um, Here are some examples of finite sets. The set of presidents of the United States. Well, at any given point in history, there's only been like so many presidents. We can count them. It's going to be a natural number. So it's a finite set. The set of planets in our solar system, right? So we think we hopefully know how many planets there are. Sometimes we go back and forth with poor Pluto. But anyway, so even if there are a couple more hiding in there, it's not going to be so many as to make it infinite, right? So that's also a finite set. All right, so what about an infinite set? Well, here's one of those definitions in math that can drive some people crazy. An infinite set is a set that is not finite. So what does that mean? That means there's no way you can describe its cardinality using just a whole number, right? So basically, an infinite set is a set whose cardinality is infinite, all right? Here are a couple of sets with whose cardinality is not finite, not a whole number. The set of whole numbers itself, right? How many elements does it have? Well, then this pattern keeps going forever. So the cardinality of the set of whole numbers is not a finite number. So therefore, we say the set of whole numbers is an infinite set. That doesn't mean infinity is one of the members of this set. No, we're talking about the number of elements. So when you talk about a finite versus an infinite set, you're not talking about the kind of members. You're talking about the number of members of that set. How about the set of solutions of this equation? Well, basically, if you look at that equation, what is it saying? It's saying I want all the numbers that I want. When I add one to themselves, I get that number plus one. Well, that's true for any number, right? What's 0 plus 1? Well, it's 1. So 0 plus 1 is 1. So it's one. It's always true, right? It's what we refer to as an identity in mathematics, right? Now, an interesting happens when you try to solve an identity like this. Let's say we go ahead and move the x's to the left side. So I'm going to go ahead and subtract x from both sides. Well, you're going to realize it's not going to move to either side. And let's say we also try to move the the numbers to the left side. So I end up doing this, right? Now, if I look at the effect of both of those actions, I end up with canceling out everywhere, right? 0, 0, 0, 0. So I end up with 0 equals 0. That, of course, is an identity itself. So if you try to solve an equation which is in actuality an identity, you're always going to get it to an always true statement like this, or an identity. So in other words, if I give you this equation and I say solve it, you're going to say, well, this is true for all real numbers. So the solution set of this this equation would be all x such that x belongs to R. And that's that. And again, of course, the set of real numbers has infinitely many elements, so it is considered an infinite set. Okay, to continue our discussion of sets, one type of set of interest to us is what's called a universal set, or the universe for short, denoted by the capital U, is basically the set of all elements being considered in a given discussion. You'll see that in context, and it'll make more sense very soon. Here's a very simple example. Suppose that we consider all the members of the US Senate, right? So U in this context would be all X such that X is a member of the US Senate. And that's, of course, in set builder notation. When it comes to a more graphic approach to sets, what we do is we denote the universal set with a large rectangle, and then the particular sets that are within that universe, we use normally circles, or we can use other geometric objects as well, figures as well, but normally we use circles. In this case, only members of the US Senate are included in the rectangle, and we call the name of such a pictorial representation a Venn diagram. So let's take a look at the Venn diagram for this scenario. So there is our universal set. Now suppose we want to represent the subgroup of this set, which is all the female senators. Then what we would do in this manner is we would put a circle inside our universal set, and then we would label it. Now, sometimes they put the labels inside like this, or sometimes they're written right outside as well. So right up, or in this case, right above. So either case is used often. All right, so one type of set which is of great interest to us is what is the complement of a set. Basically, if you're dealing with a set, such as in this picture, which is the set of females within the Senate, then of interest to us is the set of all elements that are not female. So this would basically include the males in the Senate, or non-binary as it may be referred to today. But anyway, we would basically shade everything that is outside of the female set in order to show the set of all the members of the Senate that are not females. Okay, so this green area is called the complement of the set F. F being, of course, the set of all female members of the US Senate. So basically the complement of a set A, and we write it with an A with a bar on top, is the set of all elements in the universal set U that are not in A. That is, A bar equals all X such that X belongs to U and X does not belong to A. Okay? So let's consider this example. We have the universal set U composed of the letters A, B, C, and D, and the set B containing only the elements C and D. We want to find the complement of B. We want to find the complement of U, the universal set itself, and the complement of the empty set. Now, we'll start with the complement of B. Remember, the complement of the set B is going to include all the elements in the universal set that are not in B. So what would they be? Well, B contains C and D, right? So the elements that are not in B would be A and B. All right, what about U complement? Remember, U is the entire set under study, right? So what isn't in U? Well, there is no element that is not in U, so therefore the complement of U contains no element. What's the another name for the set containing no elements? I think I heard you say the empty set, and you would be correct. All right. Remember, we can also write it like this. And what about the complement of the empty set? Well, the empty set contains no elements, so what in the universal set is not contained basically in the empty set? Well, everything else, right? So all of U. What isn't contained in the empty set? Everything that's contained in the universal set itself. So we say the complement of the empty set is the universal set itself. All right. In this next example, you have the universal set being all x such that x is an animal in the zoo. So basically all zoo animals. And S is all x such that x is a snake in the zoo, right? So what would S complement look like? In other words, what would S bar be? Well, think about it. It would be basically all the animals in the zoo that are not what? Snakes. So X such that X is an animal in the zoo that is not a snake. All right. So there's a couple of examples of complements. All right, here we have another example. Here, the universal set is the set of natural numbers. Now, while you may know exactly what that is, I strongly recommend you actually write it out. So U is the set containing 1, 2, 3, 4, write a few elements at least. Now, E is the set of all even natural numbers, and O is basically the set of all odd natural numbers. So we want to know basically what is E bar. Now notice that both E and O are contained within the universal set U. Now if you were to draw this using a Venn diagram, it would be kind of similar to this. It would be, notice that together, however, they comprise the entire set, right? So it's kind of like broken into two parts, right? You have E on one side, you have O on the other side, and you have U, right? Now, rather than writing the complement of E as a half a rectangle, sometimes people just use circles, but this is good enough. This is really descriptive of our situation here. So because E and O together completely speak for U, meaning they comprise all of U. So E bar is going to be all the elements in U that are not in E, right? So what would it be? Well, it would be all the odd numbers, right? So in other words, what is left in this set after you take out all of these guys? Well, only the odd numbers, right? So that's O. And what is O bar? I think you see where this is going, right? What are the natural numbers that are not odd, right? That's what's left over, all the natural numbers that are not odd. Well, that would be all the what? All the even numbers, right? So here we go. All right. Always spell it out. It helps to see it a little bit easier. We continue our discussion of relationships between sets, and one of the primary relationships between sets is of one set being a subset of another set. The way we write it is we write B and then this sideways U and then a bar underneath. We say B is a subset of A. And that only happens if every element of B is also an element of A, right? If that is not the case, if A is not a subset of B, we just use the same symbol and put a cross through it, right? A bar through it. Now, here is an example of a scenario like that. Suppose I have this set A and a smaller set that is completely contained within it, B. So here you can see that every element in B would also be an element in A, and that's how we say B is a subset of A, like so. Okay? As a real simple example with numbers, let's say you have the set A equals 1, 2, 3, and 7. And let's say you have the set B, which is composed of just 2 and 7. Notice that everything that's contained in B is also contained in A completely. So we say B is a subset of A. So note that the fact that B is a subset of A has no guarantee that A is a subset of B as well, and we know that it's not. So here we say, and A is not a subset of B. Think about what it would mean if A is a subset of B and B is a subset of A. Think of that for a minute, pause the video, and then come back. All right, I think that you have realized that that basically means that the two sets are what? Are equal, right? That's the only way A can be a subset of B and B can be a subset of A at the same time, right? They would have to be equal sets. Why? Because this means there's no element in A that is not in B, and this one means there's no element in B that is not in A, right? So what does that mean? Together they indicate that A and B must be the same set. So notice that the notation B is a subset of A does allow for the possibility of A and B being equal in the case that B is the subset of A and A is a subset of B. There are subsets that can never be equal, and we have a name for them. We call them proper subsets. We'll look at that next. Now, if you have a set B that is a subset of a set A, and B is not equal to A, then there's at least one element inside A that's not in B, right? In this case, we say that B is a proper subset of A. And this is the notation. Notice what we dropped. We dropped the or equal symbol bar on the bottom, right? So for a regular subset, which could allow for equality, we use that symbol, right? So this just says subset, right? B is a subset of A. But when I write B is a subset of A like that no longer should be read as B is a subset of A. This should be B is a proper subset of A. So here we say B is a proper subset of A. It kind of has to do with the notion of equality, right? And less than or greater than. So notice that when B is a subset of A, and we don't know that necessarily that they're not equal, we say the cardinality of B, right? The number of elements is in B is less than or equal to the cardinality of A, or the number of elements in A. Whereas notice here, when B is a proper subset, we know for sure there are elements in A that are not in B. So therefore, the number of B is no longer less than or possibly equal to the number of A, right? Or the cardinality of B is no longer less than or equal to the cardinality of A, but rather the cardinality of B is strictly less than the cardinality of A. All right. there's that definition that's important to us. All right, so here we have A equals the set composed of the numbers 1, 2, 3, 4, 5, and B, the set composed of the numbers 1 and 3. P suddenly is given to us in set builder notation. And we want to identify all the subset relationships that occur among these sets. So you can obviously guess that the first thing we're going to do is try to write this set in roster notation, right? Or listing notation, because it gives us a better feel for the set that way, right? So let's go ahead and write out what P is in terms of its actual members, right? Now, we know that it's all elements x such that x has this form, right? 2 to the n minus 1, where n belongs to n. So let's just run through some values, right? What if n is 1? We get 2 to the 1 minus 1, which is 1, right? What if n is 2? We get 2 squared minus 1, which is 4 minus 1, which is what? 3. What if n is 3? We get 2 cubed, which is 8 minus 1, which is 7. If it's 4, we get 2 to the 4, which is 16 minus 1 is 15. Let's go ahead and go for one more. And if it's 5, we get 2 to the 5, which is 32 minus 1 is 31. And notice this does not end because it's stated, the definition is for all n belonging to n. So this set actually keeps going. All right, so now we have a better feel for what P looks like. So given all that, what can we say is, let's go ahead and be systematic about this again. We'll talk about the relationship, subset relationships between A and B, and then between A and P, and then between B and P, right? So let's talk about A and B. Is A a subset of B? Clearly not, because there are elements in A that are not in B, right? So A is not a subset of B. But do note that B is a subset of A, right? In fact, we can do better than that. It's not just a subset of A. In fact, because there are elements in A that are not in B, it's a proper subset of A. Like so. All right, how about A and P? Is there a subset relationship? Is A a subset of P? No, it's not. Is P a subset of A? Clearly not. There is no subset relationship between A and P, right? How about B and P? Is B a subset of P? Yes, it is, right? Because you have 1 and 3, and both of them are in P as well. So B is a subset of P. Is B a proper subset of P? Yes, it's that as well. Okay? All right. There's one other subset relationship that exists between each of these sets and itself. Notice A is a subset of A. Make sure you never say that a set is a proper subset of itself, because it's not, because they're actually equal. So there are no elements in one which is not in the other. So, but you can always safely say that any set is a subset of itself, right? How about B? Yes, works for B and works for P. Again, as long as you use just a subset notation, not proper subset notation. All right, that's that. All right, also note that if you have two finite sets and their cardinalities are equal, we know that the two sets are equivalent. and that it's possible to establish a one-to-one relationship or correspondence between A and B. Now, if A is a proper subset of B, then we know that the cardinality of A, the number of elements in A, is less than the number of elements in B, which is called the cardinality of B. And therefore, it will not be possible to establish a one-to-one correspondence between the two sets. This pretty much brings us to a wrap on the lesson. At this point, as is our tradition, we're going to take a look at a couple of examples from the homework. All right, here's a good example with respect to the one-to-one correspondences and how many of them exist between two sets. Now, remember, that can only happen if two sets have the same number of elements. So if they each have 6 elements, remember that the way we figure that out is we say that we can do kind of a nice little graphic like this. We can say that, for example, let's say we have 6 slots here to deal with. 1, 2, 3, 4, 5. Okay. So let's say I want to pair the first element of the first set with one of the elements of the other set. Remember, each of them has 6 elements, right? So for so this first spot here I'm using is for the first element. How many choices do I have for pairing that element with one of the elements of the other set? Obviously 6, right? Because all the members of the other set are available in the beginning for the pairing. So 6. Now, let's say I've made that choice, right? Now I move on to the second element right here. So how many choices do I have for pairings? Remember, now one of the members of the second set is spoken for by the first member of this set, the first set. So now we only have 5 options available, right? So when we move on to the next one, we know that, so now we're trying to pair the third member of the first set, and at this point it only is left with what? 4 options, because 2 of them are already spoken for, and on, right? So you see the next one will have 3, and then 2, and then 1, right? So basically, if we, using the fundamental counting principle, if we multiply 6 by 5 by 4 by 3 by 2 by 1, we end up with the number of choices that we need. Let's see if we can do this in our head. So let's see, 6 times 5, that's a nice number, that's 30. I know that times 4 is 120, and then times 6, that should be 720. So just to be safe, you can go ahead and figure it out on a calculator. Okay, so 6 times 5 times 4 times 3 times 2 times 1 is really not needed because that's not going to change anything. So we get 720. All right. Now, as it turns out, this kind of a product is very special, where you start with some natural number and then multiply by the next natural number less than that, and then by the next natural number, etc., all the way till you end up with 1. This product is known as a factorial. So this right here would be 6 factorial. Now, on some calculators, you can actually locate that. So let me show you, for instance, on this calculator, which I highly recommend. It's available for pretty much all platforms, and it's free. Believe it or not, which is amazing. It's a great service HP is doing to all students who have to deal with a calculator. So, and you can download it either at the Windows Store or, I have to admit, I'm not positive about Macs. I haven't checked it for Macs, but I know it's available on Android as well. So Hopefully it's available for your platform. I'm pretty sure it is. So it's called HP Prime, and I think this is the light version. They have a version that's for pay, but for our purposes, you don't need anything more than this. So notice that if I click 6, I can then go to this toolbox, and then factorial is something often encountered in a probability class, so it'd be under there, and then you just click factorial, and that, notice that it's an exclamation mark. That's exactly what it is. The symbol for it is an exclamation mark, and enter it and you get that. So you don't have to sit there and what? Type all that, right? So next time you run into a situation like that, make sure to use the factorial feature of a calculator. All right, so what if each set has k elements, right? So remember, that means the first there are, when you pick the first element in the first set, it has k options available to it for pairings, right? The next one will have one less, or I mean one fewer, sorry. And the next one will have yet one less than that. So k minus 1, or 2 less than k. So k minus 2, and then k minus 3. Notice this is going to go all the way down till what? Till 2 and 1. In other words, the number of choices is going to be k times k minus 1 times k minus 2 times 3 times 2 times 1. But you recognize that? That's just what? That's a factorial. So it's going to be just k factorial. Okay. All right. So that's how you handle problems like that. All right, this is an important problem just because it really shows whether you're understanding all the symbols that are involved with respect to sets and their relationships. For example, here they say, is 0 a subset of the empty set? Well, the fact of the matter is the empty set has no element, so there is no element that can be a subset of it. But there's a bigger problem than that, and that's in notation. 0 is a number, and a number can belong to a set, but only a set can be a subset of another set. So if they had written, for example, 0 within a set like that, notice that this would still be false because there is no subset for the empty set except itself, right? But at least you wouldn't have the technical error of having written that an element is a subset. An element can't be a subset of another set. An element can either belong to a set or not belong to the set. So be careful with notation. Here's another one. Is 2187 a subset of this set, basically the powers of 3? Well, here's a very tempting approach. Okay, so you sit there and you start looking at some powers of 3. Well, powers of 3 grow pretty quickly, so we shouldn't have to spend too much time. Let's just start with, say, 3 to the 5, okay? Well, that's too small. What about 3 to the 6? We're getting better, closer. So how about 3 to the 7? There we have it. So 2187. So if you're not careful, you can get excited and go, oh yeah, 2187 is part of this group of powers of 3 with the exponent coming from the natural numbers. However, again, the problem here is format. 2187 is a number, so it's an element, it's a member. It can either belong to a set or it cannot belong to a set. Had they given us this, Had they said 2187 belongs to the set, in other words, using the epsilon notation, all x such that x equals 3 to the n for n belonging to n, then we would have said this is what? That's true. You see? This statement would now be true, but because they're saying an element is a subset of another set, we have to say false, because an element can't be a subset. What's another thing? I want you to think about how else you could have rectified this situation to where this could have been a true statement, but not using the element notation, but using set notation. How could you have written this correctly? Pause it, think, and then come back. All right, so I hope that you realize that what you would need to do is just put the 2187 into a set notation. Now the set containing 2187 is a subset of all x such that x equals 3 to the n with n belonging to n. So there are two ways we could have made that a true statement, and that's that. How about this one? 2987 is a subset of, okay, so let me ask you, do I need to even go worry about whether this relationship works, whether this number can possibly fit this relationship? Well, not really. Why? Because again, the notation is wrong. They're saying an element is a subset. However, I can ask you, can you try to fix it or see if it's fixable? Well, let's see. We want to know if 2987 can be written in the form 3n minus 1, right? So we want to know, add 1 to both sides, if 2988 equals 3n, whether this can hold for a natural number n. But then we plug it into a calculator, and so I lost that piece of information. Let me rewrite it. So we had 3n minus 1 equals 2987. Actually, let's see if no. 2987 equals 3n minus 1. So 3n equals 2988. So we're going to divide 2988 by 3 and see if that's a natural number. And it would be. So again, the problem can be rectified by simply saying, so two ways you can fix that, right? See if you can write down both of those ways for me. Pause and come back. All right. So one way is to actually use belong to notation, right? Membership notation. We can say 2987 is an element of or belongs to the set of all x such that x equals of the form 3n minus 1 for n belonging to n. Or we could have said the set containing 2987 is a subset of the set of all x such that x is of the form 3n minus 1 for n belonging to n. Okay? And that's that. All right, so the last one is X, a subset of this set. Again, we don't need to continue. X is an element, it can't be a subset. There's no need to worry about anything else. All right, so here we want to draw a Venn diagram showing the relationship between the set of natural numbers and the set of whole numbers. Remember, the set of natural numbers is this set, whereas the set of whole numbers just throws in an extra 0, right? So, as you can see, the set of natural numbers is a subset of the set of whole numbers and not the other way around. So here we have the smaller circle representing n and the larger circle representing w, the set of whole numbers, and that's the relationship between them. For this one, I just want to give you a hint. You should be able to count how many numbers there are in here without actually having to list it, right? And the way you would do that is that with the recognition that this is in fact an arithmetic sequence, right? And the same goes for this one. For this one, the common difference is 1. For this one, it's 2. So use the formula to find the element, which would be 1006 in this one or 93 in that one, and that should tell you how many terms are from here to here, which therefore gives you the cardinality of the set. And that's that. These are pretty straightforward. You should be able to guess these with no problem. All right, for this, my hint for you is write them out, okay? So write equals in front of each one of them, and then write out 3 or 4 members of each. You know, at least 3, 4, maybe even 5. The more the merrier, right? The better you'll see the relationships, okay? And then you should be able to answer those relationships very easily. All right, so here's a very nice application of the fundamental counting principle. I mean, who doesn't love ice cream, right? So here we go. So we want to know how many ways are there to stack an ice cream cone with 4 scoops if the choices are, all right, and remember, we really don't care about all these names unless we're actually at the ice cream store and going to make a very important decision of which flavors to buy. What we care about is how many different ones there are, right? So there's 1, 2, 3, 4, 5. Be careful, that's just 1, even though it's 2 words. 6, and that's also just 1, 7. So basically, here we're gonna stack the 4 scoops, right? So tell me, the first scoop that you're gonna put on top of the cone, how many choices do you have for that one? Remember, each scoop must be different. So the first one has the greatest number of choices, right? Because you haven't put anyone on yet, so 7 choices, right? Now for the next scoop, right? Remember, no repetition of scoops. Each scoop must be different. So how many choices do you have now, given that one choice has already been made for the first spot, right? You only have 6 choices, right? How about for the next one above that? These 2 flavors are spoken for. We picked one here and we picked one here. So now we only have what? 5 choices left. And finally, 4 choices left for the last one. So now all we have to do is, using the fundamental counting principle, multiply 7 by 6 by 5 by 4. Now be very careful. That is not 7 factorial. So don't use the factorial key here. This is actually 7 times 6 times 5 times 4. So we end up with 7 times 6 times 5 times 4. So we get 840 ways. Now, why didn't we end up with a factorial, right? Because we weren't making 7 choices, right? If we were making 7 scoops of ice cream on top of each other, then we would have ended up with 7 factorial ways of doing it, right? But because we only have a 4 scoop situation, then we only go up to what? From 7 to 4. All right. And this 4 has nothing to do with that 4, by the way. All right. So what if in the second scenario, what if there are no restrictions on flavor? Hey, maybe you really love pistachio ice cream and you want all 4 of them to eat that. So in other words, you can have repeats. In that case, how many possible stackings of 4 are there? Well, notice the scenario changes. So starting with the bottom scoop, right? The first scoop that you put on. How many choices do you have? 7. No restrictions on the next flavor, right? So you don't have to count out the one that's already put there yet. That's already put there. So how many choices do you have now? 7 again, right? And again, 7. Remember, no restrictions. And again, 7. So this time you're going to get a lot more possibilities because now you're going to get 7 to the power of 4 possibility. That's obviously much larger than that. So 7 to the power of 4. So 2,401 possible ways you can stack 4 scoops on top of each other. Now, with respect to this, I said don't use the factorial button, but let's say you've fallen in love with the factorial notation. You really, really want to do it, right? Can you do it? Well, especially if there are a few more. Let's say you had 8 times 8 times 9, etc. There is a clever way of using the factorial notation. So I'll show you with this. You have 7 times 6 times 5 times 4. Go think about how you would do it yourself first and then come back. All right, so the way you would actually do that would be this. What is missing so that I can end up, what would I need there to be in order to use the factorial notation? I would need times 3 times 2 times 1, right? Well, what is that now? That's now 7 factorial, right? But I can't just multiply by 3 times 2 times 1 out of the blue. I'm changing the problem. So how do I deal with that? I also divide by 3 times 2 times 1, right? So this becomes 7 factorial over 3 factorial. So if you really insist on using the factorial notation, you could do it that way. So, because remember, we multiplied by 3, by 2, by 1, and we divided by it. So these cancel out. So we didn't change the problem, we just changed the way it looks, right? So we get 7 factorial divided by 3 factorial. Oh, I didn't, oh no. Divided by, okay, what's this? Let me do this. Let me, this is also a clever way of dealing with fractions. Hit your division sign first and then change these. 7 factorial, and then we're going to go in here and put 3 factorial. And of course we end up with the same number, 840, okay? As expected. All right, so that's a nice problem. All right, so here we want to find the pairing with the set of natural numbers and the set of whole numbers to say that therefore there's a one-to-one correspondence between them, right? Now, this can get confusing sometimes because you're thinking, wait, how can that happen? How can two sets have a one-to-one correspondence when one set seems to have one more element, right? Well, that's when things get interesting when it comes to infinite sets, okay? So we know that the set of whole numbers is, well, let's start with the set of natural numbers. We know that contains 1, 2, 3, 4, right? Now, we know that the set of whole numbers has one more element in it, right? All right, so notice I can easily create a one-to-one association here. I just send 1 to 0, 2 to 1, 3 to 2, 4 to 3. So where would I send any given natural number n? I would send it to, you guessed it, n minus 1, right? So don't let this confuse you, because this happens with infinite sets. Infinite sets, even though you know for a fact one may contain more than the other, can be put into a one-to-one correspondence, because the fact of the matter is that the infinity associated with both of these sets is the same infinity. We call it aleph null. We're not really going to get into all that in this class, but there are different levels of infinity, right? For example, you wouldn't be able to create a one-to-one correspondence between the set of irrational numbers and the set of natural numbers, okay? Because even when infinities are concerned, that has a higher level of infinity than the set of natural numbers. So anyway, that's how you would do the one-to-one correspondence for these two infinite sets. It is possible to show that you can even create a one-to-one correspondence between the set of natural numbers and the set of integers, even though that one has negatives in it. This one has negatives, positives, and 0, and this one only has natural numbers in it, right? Roughly speaking, just to give you a little bit of a hint, we won't really get into it in too much detail. Think about maybe sending the positives maybe to odds, right? The negatives, send those, or maybe the other way, send the positives to evens and send the odds to the negatives, etc. So there are ways of clever ways of dealing with that as well. All right, so there's that question. All right, so this is an interesting problem because it's asking you to shade, given an A depicting a complement, you want to shade a complement. In other words, what's the complement of a set? Well, if you think about it, the complement of a set is always just going to be what? The set itself, right? So A bar is always going to be back to A itself. Think of it this way. Start with a set A, right? Let's go with their practice of writing it inside. Okay. Now, where is a complement? Remember, that's going to be all the elements that are not in A but within the universal set, right? So there's a complement, right? So now we're going to find the complement of that red part that we just shaded, right? So what is not within the shaded area? Well, that brings you back to what? Brings you back inside to A. So the red part is AC, and the green part, or I mean A bar, there's an old habit. We used to call, instead of using the bar symbol, we used to actually just put a C. So it's the same thing as A bar, okay? So A bar and the green region is now A bar bar, and as you can see, it's clearly just back to what? Back to A. Seems like they brought you a little bit of review back from the previous set. The best way to handle these is using truth tables as explained in our previous video, so make sure you take the time to do that. Don't try to answer these just by looking at them usually. It's best to explore them using truth tables. Yes, truth tables. All right, I think that's a good point to call it the day. You should have enough information to handle the homework. So take care of yourself, and I'll see you at the next lecture.